Okay. Thank you, Dr. Bezadon. Thank you, class. My name is Joshua, and I will be giving you a presentation on Ember, which is an open data set for machine learning malware classification. Ember is an open source data set for training static, portable, executable machine learning models in malware classification. It consists of 1.1 million, or I'm sorry, it was created from 1.1 million binary files consisting of 900,000 training samples and 200,000 testing samples. The training set is evenly distributed with 300,000 malicious samples, 300,000 benign samples, and 300,000 unlabeled samples. The training has a similar training set distribution with 100,000 malicious samples and 100,000 benign samples. Now, I purposely included the distribution graphic for the data set in this slide because it illustrates a specific problem that can arise in the realm of cybersecurity, which is balancing. Because as we saw from our assignments this week, an imbalanced data set can decrease the performance of a model and needs additional work to overcome, which is why it's my belief that the creators of Ember took this into account when making this data set, as you can see in the beautifully uniform distribution of the samples on the right. The purpose of Ember, it was created to fill a void in the information security / cybersecurity domain. Someone got a hot mic? Okay, sorry. Machine learning is one of the fastest rising fields in technology, with applications being developed for almost every sector and industry. Large, open, and robust data sets exist for many applications of machine learning, including image labeling, handwritten digit classification, traffic sign detection, speech recognition, etc. Unfortunately, cybersecurity is one field that doesn't have the luxury of having a wide option of data sets that are the correct combination of the attributes previously listed, which is large, open, and robust, that can be used as benchmarks until now. Enter Ember, which was created to serve as a benchmark data set for static PE malware classification. The authors hope that the data set code and baseline model provided by Ember will help invigorate machine learning research for malware detection in much the same way that benchmark data sets have advanced computer vision research. All right, creating a benchmark data set was a primary purpose of the authors of Ember, but a benchmark is a relative measurement tool. In order to gauge the efficiency of a data set and subsequent model, the result must be directly compared to a model. This is where Malcom comes into play. Malcom was a recently published end-to-end deep learning model for malware detection that Dr. Bezadon covered in his slides. And it was determined to be a suitable performance comparison and was used as a validation metric for the results of the Ember dataset. There are challenges to releasing a malware classification dataset, and the significance of Ember is overcoming these below. The first is legal restrictions. There's a ton of data sets containing malware that can be easily and openly sourced, but the problem is that the majority of these data sets are extremely unbalanced and contain few, if any, benign samples. And because benign samples are typically protected by patent and copyright law that prevents unauthorized distribution of them, as a result, many malware data sets are large and open, but not robust because they contain little to no benign samples, making them extremely imbalanced and unsuitable to be used as a benchmark. The second challenge is labeling. Unlike images, text, and speech, which may be labeled relatively quickly and in many cases by a non-expert, determining whether a binary file is malicious or benign can be a time-consuming process for even the most well-trained. And when you take it into consideration, along with the sufficient size requirement of a benchmark data set, labeling can prove to be a long and cumbersome road. The last challenge is security liabilities and precautions. There is a risk in promoting a large data set that includes malicious binaries to the general non-InfoSec audience, not accustomed to taking appropriate precautions such as sandbox hosting. As such, additional warnings, notices, and user agreements should be used to absolve the authors of any liability from the damages caused by the use of the data set by any untrained or unfamiliar individuals. All right, the project scope. Ember was created to be used for the following applications: comparing machine learning models for malware detection, quantifying model degradation and concept drift over time, researching interpretable machine learning, comparing features for malware classification, comparing featureless end-to-end deep learning, researching adversarial attacks against machine learning malware, and leveraging unlabeled samples via unsupervised learning for PE file representation or semi-supervised learning for classification. The Ember dataset consists of a collection of JSON files where each line contains a single JSON object, and then each object includes the following types of data: the SHA-256 hash of the original file as the unique identifier, a course time information with the month and year resolution that establishes an estimate of when the file was first seen. Labels with 0 for benign, 1 for malicious, and -1 for unlabeled, and 8 groups of raw features that include both parsed values as well as format agnostic histograms. Some, but not all of the features are included are as follows. The parsed features, which are 5 groups of features that are extracted after parsing the PE file, general file information, imported functions, exported functions, and section information, which includes name, size, entropy, virtual size, and a list of strings representing section characteristics. Again, I just want to show the PE file format. This format is from the earlier discussed slide where the features were extracted from. The file format is arranged with the number of standard headers followed by 1 or more sections. Headers include the common object file format that contains important information such as the type of machine for which the file is intended, the nature of the file, whether it's a DLL, executable object like JSON, the number of sections, as well as the number of symbols. Now, for the model building process consisted of vectorizing the raw features first from the PE files. The model itself is a gradient boosted decision tree model using light GBM with the default parameters of 100 trees, 31 leaves per tree, and it resulted in fewer than 10,000 tunable parameters. For those unfamiliar with light GBM, it's a fast, distributed, high-performance gradient boosted framework that's based on decision rhythm used for ranking, classification, and many other machine learning tasks. The model training time took 3 hours. It was also done on a MacBook Pro, so it's a pretty relatively simple model. Baseline model performance can be improved on appropriate hyperparameter optimization, but it's important to note that the purpose of the paper is not to showcase the model itself, but rather the data set. So model optimization was not one of the focuses of the authors. All right, for the results. We have an ROC curve, which is a receiver operating characteristic curve, and it's shown in this slide in figure 5. A receiver operating characteristic curve, or ROC curve, is the graphical plot that illustrates the diagnostic ability of a binary classifier system and its discrimination, as its discrimination threshold is varied. For the Ember model, the ROC AUC area under curve exceeds 0.99911. And there's the ROC AUC is a performance measurement for classification problems at various thresholds. The ROC is the probability curve, and the area under the curve represents the degree or measure of separability, and it tells how much the model is capable of distinguishing between the classes. At a threshold of 0.871 on the model, with less than a 0.1% false positive rate, they had a detection rate that exceeded 99%, and at less than 1% false positive rate, the model exceeded 98.2% detection rate. As a comparative study, the authors trained Malconv on the raw binaries underlying the dataset. They used the model architecture and training setup as prescribed and verified by the authors, except that they trained with a batch size of 100 instead of 256 due to GPU memory constraints. The model was trained using data parallelism across 2 Titan X Pascal GPUs. Each epoch took 25 hours. The model was trained for 10 epochs, or 10 days. The resulting model had roughly 1 million parameters. Applied to the raw binaries corresponding to the Ember Dataset, the Malconv ROC AUC is 0.99821, which is slightly less, and corresponds to a 92.2 detection rate at a false positive rate of less than 0.1%, or a 97.3 detection rate at less than 1% false positive rate. This is slightly lower performance than using the Ember Dataset using the light GMB model with no hyperparameter tuning. Evidently, despite increased model size and computational burden, featureless deep learning models have yet to eclipse the performance of models that leverage domain knowledge via parsed features. For future development, to the author's knowledge, Ember was the first data set, or represented the first large public data set for machine learning malware detection, which must include benign files. And its authors hope that the data set is useful to spur innovation in machine learning malware detection. They consider a number of research use cases, including comparing model performance, adversarial machine learning, offense and defense, semi-supervised learning for malware, and many more research areas. for the critique of the paper, overall, as a machine learning student, I found the paper, it's very interesting. It was well presented. I like that the authors added on the sample code alongside the data set because it offered transparency as well as reproducibility in validating their results. But the critiques I would have is that the first is that the data set's performance was based on one model, and that was the light GMB model. And yeah, I would have liked to see more than one model tested. And although the author specifically stated the purpose of the paper was to introduce the Ember dataset, not a particular model, I personally feel that including more than one model would help validate their findings. And then the second critique is that there was only one measure of validation. The performance was compared to Malconv, and again, performance comparison is a crucial validation tool, but I would like to see how the model performs against more than one established application of malware detection. This is the paper that my presentation is based on, and that is it. Does anyone have any questions?
Thank you very much, Joshua, for this excellent presentation. I'd actually attended earlier presentations by the original authors of Ember, and I found your presentation to be at the same level, if not better, in terms of the amount of information it conveys. Now, before I pose my questions or comments, does anybody want to say anything about this work? Does anybody have any questions or thoughts on Ember? Okay. So my first seed question is, first of all, Joshua, can you tell us if you saw anything about measuring the representativeness of the data set in the paper? Do the authors talk about how representative the data set is of the actual malware observable in the real world?
No, I don't recall ever seeing any mention by that. They briefly describe basically just the structure of the data set, but they don't go into any more detail other than that.
Well, thank you. That's what I remember from Ember. And this is a very core and fundamental question / problem. How can we measure how representative a data set is? How representative of the real world a data set is? Does anybody have any thoughts on that? Joshua, do you have any thoughts on this?
I'm thinking it's a very, very good question. I'm currently formulating a response, but give me 20 seconds and I'll have an answer for you.
Sure.
If someone else wants to, feel free to jump in while I'm thinking.
Nancy has an answer. Nancy, would you like to share it with us?
So in general, when we want to represent a population for statistical inference, we do random sampling. But the selection of what we can offer to the public with these confidential network logs is a complication, I guess. Like what data logs you could offer to the public may not even represent the kind of things you would want for to actually evaluate a malware for a malware detection. I'm not sure though.
So the assumption is this data set is sampled from data available in the real world. It is as close to random sampling as practically possible. And that's a claim of the authors. Now that we have sampled our data, how can we check to see if it's representative? So what does it mean for a data set to be representative? Venu, you have some thoughts on this? Would you like to share it with the class?
Yes, with all the possible malware attacks, if the data is then randomly sampled, we later check out in the same way which Joshua has presented, with all the kinds of malware attacks being representative in equal amounts.
That's a good point. That's a very good point. The problem is not all types of malware occur equally, and it changes over time. So, yes?
Then based on the amount or ratio of how the attacks occur, suppose if one kind of malware is of 4 times of what a different malware attack happens, we take in the data in such amount of ratios.
So this is an interesting idea. Look at the statistics available from studies on malware infections in the real world and see whether we can reproduce the same statistics from the data set. But that only refers to the type of malware, not the inner workings of the malware, the byte representation or the PE header representation of the malware. That remains a problem. Akhil, you have some thoughts as well. Would you like to share it with us?
Yeah, so for the representation of the data set, like we need a particular specifications for each and every attribute for the proper representation of the data set, so we can, carry forward with the problem, as in like malware detection, etc.
Well, that's another interesting point. Are the attributes recorded in this data set sufficient and representative of what's out there? But this is still not enough. I have 2 raw ideas. I haven't done any research on this particular problem myself, but I have 2 raw ideas. One idea is to keep collecting samples over time, adding them to the data set, and checking the distributional drift of the data set, checking to see how much the distribution of data in the data set changes. If it changes significantly over time, over a short period of time with more samples added to the data set, it probably means that the original data set was not very representative of what we've been dealing in the real world, because adding more samples has changed the distribution of data, meaning that the original distribution did not accurately, sufficiently, did not represent the real distribution with sufficient accuracy. Another approach is more practical. It's based on the notion of representativeness. It's an objective definition. We want a representative data set because we want a classifier trained on this data set to be applicable to real world samples, right? If we train a classifier that does very well on the data set, both at training time and at test time, we can deploy that classifier in the settings of the real world and measure its performance over a short period of time and see how well it does. If it does well or as expected, it means that the data set is representative of the malware problems we deal with in the real world. If it's not, if there is a major difference between the deployment time performance and the test time performance of the data set, we can conclude that one of the possible reasons is that the data set is not representative. Another possible reason is that our model is overfitted, or our model does not is not equipped to capture the complexities of malware data. Why do I keep repeating the term short term in testing these or adding samples collected over a short period of time or testing the model over a short period of time? Because if you expand the time span of this experiment, if you extend it to, let's say, a year or 2 years, then the nature of malware changes over that time as well, right? It changes, for example, between 2014 and 2016, ransomware became a real serious phenomenon, and we did not have samples of ransomware in our data set. Of course, this also means that our data set is not representative enough for new samples. But for now that we have this data set and we want to do a static analysis of how representative it is, we have to limit the time span of the analysis. And there's also a lesson in this. Any classifier that you train, any machine learning model that you train on security data will be obsolete over time. How fast does it move towards being obsolete? It depends on the type of data that you are looking at. And of course, it depends on the speed of evolution of different types of attacks and different types of malware. Nancy has a question. She says, is it like doing some sort of hypothesis testing to see if the mean of each feature drifts not due to noise? Well, you can actually measure the distributional drift. You can check, there are metrics that measure the drift in the data distribution. Another way to look at it is now you have two distributions and you want to see what the difference between these two distributions is. You want to measure the difference. Do you happen to know a good metric for this, Nancy? You have probably encountered this in your other data science classes. Just in case you don't remember, we've looked at KL divergence. KL divergence can give us a measure of how similar or how different two distributions are from each other. And there are other metrics for distributional drifts as well. Nancy, can you expand on your final question via audio?
You mean in regards to the paired hypothesis testing? Or I think there was another name for it, T something, but I just think of it as if you have two distributions of data, then what you're doing is you're trying to figure out if the distance between these two distributions of data is due to by chance, like random noise, or if there's an actual meaning between the differences. Like say like females and males, the distribution of I don't know, their weights or something like that. You would say statistically, you know, like significance that the distribution between males is a lot more. It is significantly different than females on the general ideal, but you can do a testing for it to prove it.
That's a very interesting idea. I had not thought of this before. Yes, when you measure the difference between two distributions, you may also be able to apply hypothesis testing, like pair hypothesis testing, to see whether this difference is significant or not. Is it due to noise or not? Now, Nancy, do you have any thoughts on possible sources of noise in this process specifically?
Do you mean like noise in the data itself?
Where could this noise come from? We know that noise is also interpretable, right? Where can this noise come from?
I don't think I have a sufficient answer to say that, but I think that it depends on the information you're pulling from the data, that there's obviously data that's more meaningful than others and other trivial data. I don't know if you would consider trivial data that doesn't add to the significance of the model noise, but I think it certainly makes it a more difficult, complex model to use.
That's another interesting point. Not all the features stored in this data set are necessarily useful. They can be, as Nancy puts it, trivial or redundant. However, back to my primary question, what can be the source of noise in this distribution, in this process? One potential source of noise that comes to my mind is labeling errors, occasional labeling errors. Another is corrupted data. What else can cause this? Outliers, potentially. Good answer, Akhil. Joshua?
Human error.
Human error in what sense?
And it could be labeling, data gathering, really anything.
Yes, so it can be also due to the sampling mechanism. If we just sample malware infections occurring in, let's say, Saudi Arabia, we are not looking at the grander view of things that are happening. There are particular types of malware going around in particular parts of the world. And if you only collect malware samples that were detected during daytime or business hours, we fail to collect samples that target personal users. So yes, sampling or sampling methodology can give rise to noise or error as well. So before I end this discussion, does anybody have any other thoughts, comments, or questions about Ember or ideas we talked about in this discussion? Very well. So I'm going to stop this